All right, it's Tuesday here, Physics 1151. We are going into chapter 26 today. A lot of this chapter concerns the relationships between the electric potential and the electric field. We've been discussing both of these for the last few chapters, but they both may seem to be kind of abstract concepts, and we haven't really tied together the two. And so, in the first part of this chapter, we're going to do that. We're going to study the relationships between the electric potential, which we call voltage, and the electric field. And then we're going to get into a little bit of batteries and sources of voltage and after that. And then we're going to study capacitors a little more. And this is going to form the beginning of our discussion of circuits. And we're going to get more into circuits in the next chapter. So this is starting to bridge the gap between the theoretical, which the electric fields and electric forces, and some of the practical aspects, namely voltage, current, resistance in applications and circuits. So homework 8 will be due Friday the 19th at 11:59 p.m. I think that's 7. I think that's a typo. So homework 7 is due the 19th. Homework 8 I haven't put out yet. Homework 8 will deal with this chapter. So this should be homework 7, and then we'll have quiz 3 next Monday, and that will be concern homework 7, which you're turning in on Friday. So let's get into it. So potential. Last chapter we introduced this concept of potential, aka voltage, and electric field we introduced in the previous chapter. And really what both of these are there two different but completely consistent ways of expressing how source charges alter the space around them. And so we said that source charges create an electric field, which is a force per charge that's exerted on the charges. And we also said that these charges create an electric potential or a voltage, which is related to the potential energy per charge. And so what we're going to talk about here is how we can get one of the two, either electric field or voltage, if we know the other. In other words, how are they related? So let's quickly go back and review a little bit here. So recall that the electric potential, the potential difference between 2 points, S initial and S final, the difference is related to the work done by the electric field. Okay, this was from the last chapter. And so work done by the electric field leads to differences in potential energy. And then we plugged in our definition of work, where work is equal to the force, the dot product of the force and the displacement, which is just equal to the force times the displacement ds times the cosine between the force and the displacement. And we saw that usually in our cases, the electric field was either perpendicular to the displacement, which case these are parallel, and cosine of theta is 0, cosine of theta is 1 if theta is 0, or if the electric field is anti-parallel to the displacement, then theta is 180 degrees, and this is negative 1. Now, they can be any angle in between, but in the applications that we were discussing, usually they were either parallel or they were anti-parallel. So now if we plug in what the equation is for the electric force, it's the electric field, E, times the charge, Q, so we plug that in for force, and we get that the change in the electric potential energy is the negative of the electric force, QE, dotted into ds, or in other words, the force QE times the displacement ds times the cosine of the angle between the force and the displacement. Okay, Now if we divide both sides of this equation here by the charge Q, so the left-hand side becomes delta U electrical over Q is equal to the electric potential energy per charge. That is by definition the potential or the voltage. And so this equation up here becomes delta V, which is V final minus V initial. In other words, the change in the potential is the negative work per charge, which is the dot product of E dot ds integrated over the displacement of the charge. So in other words, the potential difference between 2 points is related to the electric field that did the work in moving the charge between the 2 points. Okay, and so the electric work per charge, which is negative E dot ds, leads to the potential difference. So mathematically what this says is that the potential difference between any 2 points, S final and S initial, typo, the potential difference is equal to the area under the curve of E versus S multiplied by cosine. So usually this is either 1 or negative 1. So what does this mean here? Well, if E is parallel to displacement, in other words, if we're going along the direction of the field, then theta is 0, cosine of theta is 1. This integral becomes a positive value because everything in it is positive. So you get positive area under the curve with a negative sign. And so in other words, if we're going along the direction of the electric field, delta V is negative. In other words, the voltage decreases. Okay, so voltage decreases as you move along the direction of the electric field. If E is anti-parallel to ds, then, or if E is anti-parallel to ds, then cosine of theta is negative 1. Your area under the curve is negative. Negative times negative is positive. And so in other words, if a charge is moving in the opposite direction of the field, then the potential increases. So positive charges are going downhill if they're in the direction of the field, and positive charges are moving uphill to a higher potential if they're going against the field. Okay? But the main point here right now is that if we know the electric field and how it varies with position, we can integrate this equation, and the potential difference is the area under the curve of the electric field versus S. So let's do an example with a point charge, okay? So the point charge, remember, creates an electric field if it's a charge Q. The electric field is Q over 4 pi epsilon naught r squared, okay? And it points radially outward, away from the charge, okay? So what we want to do now is we want to calculate the potential difference between some distance r from the charge and infinity, because at infinity the electric field is 0, right? There's going to be no effect on the charge at infinity. Okay, so we need to do an integral here. In other words, if we're going to calculate the work per charge to get the potential difference, we need to integrate from r to infinity. What do we integrate? Well, the electric field, we have to plug in what E is. E is equal to Q over 4 pi epsilon naught r squared, and it's in the r direction. Okay, what is dr? What direction is the displacement? Well, if we're moving radially out toward infinity, then dr is also in the radial direction, and so ds is equal to dr in the r direction. So we plug that in for ds, and we get this as our integral. Okay. Now r dotted with r, remember by definition of the dot product, these are both unit vectors of magnitude 1. The dot product says that the dot product of two vectors is the magnitude of the first, which is 1, times the magnitude of the second, which is 1, times the cosine of the angle in between. Well, they're in the same direction, so theta is 0. And so the unit vector r dotted with r is 1. And so we're left with this integral of q over 4 pi epsilon naught r squared dr. Okay, now q is a constant and 4 pi epsilon naught is a constant, so we can pull that out of the integral. And now we've got the integral of dr over r squared. Okay, and we know that the antiderivative of 1 over r squared is negative 1 over r. And so we evaluate negative 1 over r at the two endpoints. Okay, negative 1 over infinity is 0. Negative 1 over r is 1 over r. Negative 1 over r. And so then this becomes the result of the work per charge. Okay, 1 over infinity is 0. Negative and a negative are a positive. And we get that the work per charge is equal to q over 4 pi epsilon naught r. Okay. Now we equate that. The negative of this is the potential difference between the endpoints, v infinity minus vr. Okay. V infinity is just 0 because there's no effect at infinity. That's where we've defined our 0 voltage because there's no effect of this point charge at 0. So then negative VR becomes negative Q over 4 pi epsilon R. And so we have an equation here for the potential due to a point charge, which is Q over 4 pi epsilon naught R. Okay. And we derived this in the previous chapter, but this is just using the electric field to derive it. Okay, so if you ever have a mathematical equation for the field, we can plug that in and we take the area under the curve of E dot ds, and that gives us the potential difference. Okay, let's do another example. Let's find the potential difference between the two plates of a parallel plate capacitor. Okay. Now, we derived in chapter 23, we know the electric field, okay, between here. We know that the electric field is equal to the charge per area, in other words, the area charge density in two dimensions, charge per area divided by epsilon naught. In other words, the electric field between the plates is constant and it points from positive toward negative. Okay? So let's integrate that. We know what the electric field is. What we want to do now is get the potential difference between the two plates of the capacitor. In other words, the voltage difference between the plus and the minus plates. So to do that, we take the expression for the electric field and we plug it in to the integral. And since we're trying to find the difference in going from plus to minus, our ds is going to be going from the plus plate to the minus plate. Okay. And if you notice, the displacement ds is in the same direction of the field. So the dot product, E dot ds, is E ds, and the angle between the displacement and the field is 0, because they're in the same direction. Cosine of 0 is 1. Okay. And now we plug this in right here, and we're going from the plus plate to the minus plate. So that's where our integral is. Electric field is Q over A epsilon naught times ds times cosine of 0, which is 1. These are all constants, Q over A epsilon naught, so we can pull them out of the integral. And we've got a super easy integral here, where this is just the distance, ds is integrated from the plates, is just this distance d between the plates. The integral of ds from across a distance d is just d, okay? And so delta v is equal to all of this, negative Q over A epsilon naught times D. Okay. And so in this case, we can plug, if we wanted, we can plug back in Q over A epsilon naught as E, and we get the familiar equation that the potential difference from the minus plate to the plus plate is equal to negative ed, ED, and therefore if we were to flip it, because usually we want the potential difference as V plus minus V minus, it's just positive ED, which is equal to Q over epsilon naught AD. Okay, so potential difference between the plates of the capacitor is just our favorite, Ed. Remember, we all have a relative or friend named Ed. So this is an easy equation to remember. Is delta V is equal to Ed. Okay, and then we plug in what Ed is. E is Q over epsilon naught A. Okay. So what this says is that the voltage difference between the two plates of a capacitor, which is electric field times D, depends only on how much charge per area we put on the plates and what the separation of the plates is. And so that determines the voltage across a parallel plate capacitor. Later on, we're going to see that we can put a little chunk of insulation in here instead of air, and then this gets slightly modified. But right now, this is for two parallel plates with air. So anyway, the main gist of this is not just to derive this equation using a different method, but it's to show how if we know the electric field, that the potential difference is just the integral of the electric field dotted with ds. So here's an example. We're going to do lots of examples here today because this is a little bit abstract. So we have, if we know the electric field in this problem is pointing to the right along the x-axis, and we know that the field is of magnitude 1,000 volts per meter, pointing along x, what is the potential difference between x is 10 centimeters and x is 30 centimeters? Okay, so what we need to do then is we need to plug in that E is a constant. It's 1,000 volts per meter. E is in the same direction as ds because we're going from 10 to 30, and that's along the direction of E. So cosine of theta is 1, and so this integral is just EDS from 10 to 30. We plug that back in and we get the same integral here. It's just the electric field times the displacement, delta S, with a negative. So you plug that in and you get negative with a negative in front, 1,000 volts per meter, and the times 30 minus 10, which is 20, and we get that the field is 20,000 volts per centimeter. 20,000 volts per centimeter, or 2,000 times 100 centimeters per meter, and we get that the potential difference between the 2 points is negative 200 volts. Okay, so let's look and double check and make sure our negative sign is right, that we didn't mess up a sign. So go back here. Well, we're going in the direction of the electric field. We're going from 10 to 30, and so the potential always decreases along the direction of the field, and so the difference should be negative, right? Yeah. So it's less at 30 than it is at 10. Okay. So let's do yet another example. Okay, sometimes you're given the area under the curve of E versus ds, and so here we're not given a mathematical equation for E, but we're given a graph of how the electric field in the x direction varies with x. Okay, so here we've got to do the area under the curve, And so the voltage at 3 meters minus the voltage at the origin, the difference is equal to the negative of the area under this curve. Okay? And since we're going from 0 to 3 meters, we're going in the positive x direction, which is in the direction of the field because it's Ex is positive. So cosine of theta is 1. And so our integral is just E ds from 0 to 3. Okay, well, from the figure, now we have to calculate the area under the curve. And so the area is equal to the sum of the area of a square going from 0 to 2 meters plus the area of this triangle going from 2 to 3. Okay, the area of the square has a height of 200 volts per meter, and it has a base of 2 meters, and so this is equal to 400 volts is the area of this from 0 to 2. The area from 2 to 3 is a triangle, so 1/2 base times height. Height is 200 volts per meter, base is 1 meter, multiply by 1/2, and the area here is another 100 volts. And so what this says is that the potential difference between 0 and 3 meters is 500 volts. Okay. Now the question doesn't ask that. It says, what's the potential at 3 meters? So the potential at 3 meters is whatever it is at 0 meters plus delta V. We're given that it's negative 50 volts at 0. The change from 0 to 3, it drops by 500 volts. And so the potential at 3 meters is negative 550 volts. Okay. So this is an example of how to calculate the potential difference or the potential if you're given the area under the curve of the electric field instead of a mathematical equation like we had up here for a parallel plate capacitor, or for a point charge we had mathematical equations that we plugged in. Sometimes you're not going to be given the equation, but you're going to be given a graph. And we can still, it's the same thing. It's just we're calculating the area under the graph as opposed to integrating analytically using the mathematical equation for E. So these are all different ways of getting the potential or the potential difference if we know the electric field. They're related. If you know one, you know the other. Okay, now, often in practice, it's much easier to know in the real world what the voltage is or what the potential is at these different points than it is to know what the field is. And so now we're going to go backwards, and we want to know how to calculate the electric field if we know the potential, which we can measure. Okay. So to do this, we take this little picture right here, and recall that the work done by the electric field is negative force, which is QE, dotted with ds. Okay. Now, if this delta S, if this is so small that the electric field is a constant, then the integral just becomes negative QE dotted with delta S, because E is constant over this little region, is negative QE delta S cosine of theta. And in this case, delta S is parallel to the S component along the S direction, ES. So in other words, this could be EX or EY or EZ. What we can do here is this is equal to ES, the component along the displacement, times delta S. So we plug that in, and we know that the potential difference is the negative of this work, which is this, divided by the charge Q, which means Q cancels out, and it means delta V is equal to negative E delta S. And so then we can divide both sides by delta S, and we get that the component of an electric field along some direction S, which is ES, is equal to the change in the voltage divided by delta S. And if this limit, if we take the limit as this delta S approaches 0, this differential becomes a derivative, and we get that ES is equal to negative dVds. And so what that's saying is that if we know the mathematical equation for the voltage, or we have a plot of voltage versus S, where S could be the X direction, the Y, the Z, then that component of the electric field is just the derivative of V with respect to that direction. In other words, just as the voltage, the voltage is related to the area under the curve of the electric field is related to the slope or the derivative of the plot of voltage versus S. And so, since S can be any direction, in many cases the electric field will be along the radial direction. Here's an example, point charge, go back here. Electric field is radially outward, so it's in the R direction, radial direction. Then we know that the electric field only has an R component, and so we can write ER is equal to negative dV dR for an electric field along the radial direction. And so this is point charges in a charged sphere. Okay, often you'll have in rectangular coordinates, E could have an X component, which would be negative dV dx is EX. E could have a Y component, which is negative dV dy, and E could have a Z component, which is negative dV dz. And so this, if we know how the voltage changes in any of these three directions, X, Y, or Z, we can get that component of the electric field. And in general, E could have all three components. E could have an X component, a Y component, or a Z component. And so we can write E as the X component along the I direction, which is the X, EY along the J direction, and EZ along K. And you plug these in. And what this is mathematically is this mathematical expression is called the gradient. And you may have seen the gradient in Calc 2 or Calc 3, and that's denoted by this symbol del, which is this V with a top on here. Looks like an upside down triangle. And so what that says is that in general, the electric field is the negative of the gradient of the potential. So the potential is related to the integral of the electric field. The electric field is related to the derivative of the potential. It's just like calculus, where you have derivatives and antiderivatives. You go in one direction to integrate, you go in the other direction to differentiate. And so if we know the voltage or the potential at all points, we just take the gradient, taking derivatives, and we can get the electric field. So let's again do some examples here. So let's suppose that we know the mathematical equation for how the voltage depends on position. And so in this case, V is 100 volts times e to the negative 2x. Okay. So in this case, the voltage only depends on x. Okay. It changes in the x direction. It has no dependence on y, and it has no dependence on z. And so the question is, given the equation for the voltage, how do we calculate the electric field at x equals 1 meter? So, well, the x component of Ex is negative dV dx. And so if you take the derivative of this equation, it's equal to 100 times derivative of an exponential. Here is just negative 2e to the negative 2x. And so that brings out a negative 2. And so this gives us our mathematical equation for the x component of the electric field. It's just negative dV dx. So it's negative 200 e to the negative 2x. And V is in volts, x is in meter. Electric field is in volts per meter, as it should. Okay. Now we evaluate this at x equals 1 meter. So plugging in 1 for x gives e to the 1 times 2 is 2. E to the negative 2 is 0.135. 0.135 times 200. That gives us that the x component of the field at x equals 1 meter, Ex is negative 27 volts per meter. Or in other words, it's pointing along the negative x direction and has a magnitude of 27 volts per meter. Okay? Now we can calculate Ey. Ey is equal to negative dV dy, but V has no dependence on y, and so if you take the derivative of this with respect to y, it's just 0, so negative dV dy is 0, Ey is 0. Ez, the z component of the electric field, is negative dV dz. Once again, there's no z dependence of the voltage, and so dV dz is 0, and you get that the electric field only has a component along the x direction. And so in other words, E points in the negative x direction, and its magnitude is 27 volts per meter. Okay? So this is how you get the electric field if we know the potential, the mathematical equation. Okay? Let's do another way of calculating the electric field. Okay, suppose we don't have a mathematical equation, but suppose we're given a plot of the equipotentials. Recall from the last chapter 25 that these dotted lines are called equipotentials. They're the surface of all the points that have the same voltage. So for example, along this circle right here, all of the points on this circle have a voltage of 25 volts. All of the points along this circle, this is another equipotential, have a voltage of 0. All of the points along this circle have V equals 50 volts, and all of the points along this circle have V equals 75 volts. Okay. And now if you recall from the last chapter that, and from the beginning of this chapter today, that the electric field is perpendicular to the equipotentials, and it points from more positive V toward less positive V. So it points downhill. Okay. So what we want to do is we want to first calculate the electric field at point 1. Okay, so we look at this, and the electric field is perpendicular to the equipotential, and so the electric field points in the negative r direction. It points in the radial direction toward the origin. So in the negative r direction, okay? And so the electric field is negative dV dr. Okay? Now in this case, we're not given we're given differentials. We're not giving, this is not infinitesimally small, okay? So what we do here is we know that the electric field goes from 75 volts at this distance right here to 50 volts here to 25 volts here. Or in other words, the electric field decreases by 50 volts from 75 to 25 over a distance of 2 centimeters, because each square is 1 centimeter. And so it changes by 50 volts over 2 centimeters, or in other words, it decreases by 25 volts for every centimeter. And in fact, you can see that here, right? 1 centimeter, it goes down 25 volts. Another centimeter, it goes down another 25 volts. Another centimeter, it goes down another 25 volts. And so the electric field points in the negative R direction toward the origin, and it has a magnitude of 25 volts per centimeter, or negative 2,500 volts per meter. Okay? So the electric field at point 1 is negative 2,500 volts per meter. Okay? Now let's look at point 2. Okay? Well, at point 2, the electric potential is 50 volts, and here it's 75 volts, here it's 25 volts. Okay, so the equipotentials are circles, the electric field is perpendicular, and it points downhill from higher V to lower V. And so the electric field at point 2 must be pointing radially inward as well in the negative R direction. What's its magnitude? Well, over a distance of 1 centimeter, which is about 1 square, and going from this equipotential to the next, the electric field strength has changed. It's decreased by 25, 75 minus 50. How far? It's 1 centimeter. So it's decreased by 50 volts over a distance of 1 centimeter. So the electric field, the derivative or the slope, is negative 50, this should be volts, negative 50 volts per centimeter, or negative 5,000 volts per meter. Okay. So this is how, if you know the equipotentials, in other words, the surfaces of constant voltage, the electric field is perpendicular to the equipotentials. Remember, it always points downhill from high potential to low, so it's pointing inward in this case. And its magnitude is equal to delta V over delta R. In this case, again, it changes by 25 volts over a distance of 1 centimeter. So it's 25 volts per centimeter, or 50 volts per centimeter, I'm sorry. Because you're going from 75 to 25 here as we go from this to this. So one very important point here is that the electric field is stronger at point 2, it's by a factor of 2, than it is at point 1. And you also see that the equipotentials are closer together at point 2 than it is at point 1. Okay, this is not a coincidence. In fact, in general, the electric field is strongest where the equipotentials are closest together. And if any of you have ever taken a meteorology course or are doing any environmental science, and you've taken any weather courses or you watch the Weather Channel, you might have heard them say that the winds are strongest where the isobars are the closest together. Isobars are the same as equipotentials, only isobars are surfaces of constant pressure, whereas equipotentials are surfaces of constant potential. So just like the winds are strongest where the isobars are closest, the electric field is strongest where the equipotentials are closest. Okay, so on an exam or in a quiz, you should also be able to look at this graph of equipotentials and calculate the magnitude and the direction of the electric field from the equipotentials, just like you should from a mathematical expression, taking the derivative of the equation. Here you're just doing a differential using the equipotentials. Now there's another example that I'm going to give you on the homework where you can look at, if you have a plot of V versus R, the voltage versus R, that the electric field along a given direction is just the derivative, which is just the slope of that plot, the slope of that line at a given point. So after today, you should be able to take derivatives or differentials to get the electric field from the potential, and you should be able to do integrals or area under the curve to get the potential from the electric field. This is usually more practical because it's much easier to deal with, to get the voltages or the potential field and then take the derivative and get the electric field from that than it is to go the other way. So that's pretty much it for today. This is Tuesday, and we'll see you tomorrow. We're going to go on to discuss voltage a little more, and then we'll get into capacitors on Thursday. This, remember, is our last chapter. Chapter 26 is the last chapter of Unit 2. Exam will be Monday the 29th. So have a good night.